Well, welcome to our structural modeling video conference for March of 2018. Today we'll be covering a subject that sets the context at a little higher level for structural modeling, and it's Technical Report 19, which is a general systems context for structural modeling. And the plan for this specific video conference, just kind of walk through at a general high level of the paper, and then talk about any specific ideas or elements that are of interest as we go through. Well, one of Kevin's not able to make it today because of the storm on the East Coast, so he'll indicate he'll be responding to the video, or we'll have another video session with Kevin, so we'll kind of adapt to that specific communication problem as we go. So today we're talking about general systems context and systems interaction, systems communication. And one of the primary discriminators when we start talking about systems in science and structures of social interaction is basically, do these ideas or these professions or these types of groups of people, do they look backwards in time to find key values and decision-making criteria, or do they look forward, predicting future configurations and value propositions? Of course, law is one thing that looks backwards, and of course, history and accounting, and then science and mathematics, engineering, and so forth, looks forward, tries to predict future value, and so forth. And these are two really different types of approaches for truth and looking and understanding things, and their impact. It's good to understand and lay out these areas when you're going forward and talking about large-scale socio-technical systems, because they have aspects of both, and the approach needs to, that general approach needs to recognize that and move forward. And of course, the other thing that's involved with these large-scale systems is there's always people, and we really need to be sensitive to the limits of human conception and the human mind and what's going on. The human mind basically has limits on logic and limits on communication, and can be overloaded in many different ways. So you need to be sensitive to that and make sure that you tailor your messages and your languages and so forth to not overload the human beings and emphasize different communication pathways. So the basis for effective management, of course, of large-scale systems is, first you have to identify the components, evaluate their structure and relationships, and of course, and clarify and communicate the system structure and behavior. And in structural modeling, we focus on this identifying the structure of an unknown or poorly defined system. There's a relationship between the system structure and the system behavior, but we don't emphasize that in the early on parts of structural modeling. And as a matter of fact, and as a follow-on to what we're going to be doing here in the next couple of technical reports, I'm going to try to emphasize a little bit more and explore a little bit more the concept, the differences between system discovery and systems design. And so what are the activities that you engage in when you're discovering the system, and what are the activities you engage in when you're designing a system? And the idea is, the objective is to further develop these ideas around those two fundamental human activities, either discovery or design. Okay. And of course, Warfield, in his work on the science of generic design, basically did an application of formal logic for the evaluation process. You want to really use that to minimize resource utilization. So you can discover truth in two ways. You can use logic to infer the truth, or you can expend resources and go have empirical experiments or do surveys and get the information in an empirical manner. So really one of the things that we want to do is minimize the resource utilization by maximizing the use of inference and logic. And then the other area is to the proper alignment of human reasoning capability with formal mathematical techniques. As I mentioned earlier, human beings have well-known limits on what they can do. So it's important to take these human limits into the design and the consideration when you're designing your approach to communicating systems and systems theory. So we're going to start a discussion about general systems theory by addressing a passage from Boulding that was in the preface of Clare's introduction, I guess the introduction to general systems theory. And as Clare pointed out, there's many different ways, many different approaches to general systems theory, but they all appear to have common goals and objectives. And to illustrate the common goals and objectives, Clare presented this section here that's in italics from Boulding, the 1956 passage. And basically, in reading this, the first time through, it's kind of interesting, but it presents some cognitive dissonance at first for me anyway when I read it, because I didn't, the level of theoretical model building, and that lies somewhere between generalized constructs of pure mathematics and specific theories of specialized disciplines. Well, what really, those are very fuzzy boundaries, right? And then because in a sense, mathematics contains all theories, it contains none. So, well, really, what does that mean? In what sense does mathematics contain all theories? And so, going through and looking at this, it became one of the ways of maybe discussing and looking at this a little more is to understand that mathematics is a formal system and a formal language, and that unlike a natural language, you don't need any specific context to determine whether or not statements in this language are true or false. So that the formal aspects of mathematics kind of help things here. And we went through and talked a little bit about the specific areas like biology and chemistry, physics and economics, and that they all have very specific things, but that's a natural language approach. In fact, these people build their own languages, like medicine has their own ontologies, physics and chemistry folks, biology, so that there's very specialized application languages that introduce specific definitions of terms and context. For example, the idea of definition of an idea or a concept by intention is one use of the word intention, but the medical world, right, the profession uses the word intention to say that, well, wounds heal by intention. So there's the word intention is determined, the semantics. What does it mean? It's determined in context, in that natural language idea, so that when we're having human beings are very, very good at understanding the semantics of a statement given in the context. But mathematics does not rely on the context to determine the semantics. Okay, so then we looked at the general systems theory and the approach that was set by Boulding. We said, well, basically there's three sections: mathematics, general systems theory, and specialized discipline. And then we noticed that those three sections align fairly well with the structural modeling section. And the ideas of these languages that we're talking about, formal languages, informal languages, were addressed in detail by Warfield in the Science of Generic Design. And basically there's two components to this. One is that there's a dyad of meta language and object language, which Warfield incorporated and adapted from Hilbert. And a carefully designed object language may be augmented with natural language serving as the meta language. So it's not all of mathematics that would be used for a systems language. It's a carefully designed object language or component of mathematics that may be augmented with natural language serving as the meta language. And then that natural language semantics and components also need to have maybe not necessarily careful design, but they need to have a common understanding or common semantics, like a dictionary of systems concepts or something. So there's those types of ideas here that are coming into play between structural modeling and general systems theory. This graphic, this figure, just shows the components where we have the Boulding context, of course, is mathematics, general systems theory in the middle, and then specialized disciplines on the other side. Whereas in the structural modeling context, we place structural integration modeling in the middle. Basic structural modeling or mathematics models are on one side, and interpretive structural models are real-world, substantive, empirical models of specialized discipline on the other side. So what we're suggesting here for mathematics, and what we're suggesting here for this approach, is that the mathematical theory itself is the object language. And we don't do the complete object language. We just, well, there's the complete object language from the general system, from the Moorfield's point of view, but it's all of mathematics is basically on that side. And then the interpretive structural modeling piece has the formal mathematics from general systems, which is the integration piece, which applies to more than one specialty discipline. It has some type of natural language or informal component which you use to describe that object language. And then you have another specialized object language, which is for the specialized discipline. So we can start to now look at each, in the specialized disciplines, we'll have actually like three types of mathematical object languages. One that's associated with all of mathematics, one that's associated with the general systems theory, and then one that's associated specifically with the specialized discipline. And each of those are interpreted using a meta language which is tuned for that specific object language. So that's kind of the larger conceptual idea there. We hope to, in the next couple of months, get some specific examples of this from a context of systems theory. So each language type has unique features, and these features are discussed, in the terms of, are they formal types of values? Are they factual? Well, are they Are they formal features, factual features, or truth value features? And as we go through and look at this, we'll find that the types of truth for a formal type of...
Joe?
Yeah.
Hi. So it looks like Helena's joined us. That's great.
Yes, sorry for that. Sometimes, you know, you think things work and then they don't, so.
Okay.
It's all okay. It's all good.
Okay.
So I had a bunch of comments or questions as you were going along. I hesitated to interrupt you because I wanted you to have a a coherent introduction of this new level of working. But I wonder if we should go back, or should we maybe stop at maybe go forward a little more, and then recap and start from the beginning again with the questions?
Whatever you'd like to do, Janet, it's fine with me. This is,
Okay.
if you want to interject them now, we can go forward.
Yeah, I guess
you're most comfortable.
Maybe before we get to the types of truth, maybe let's start over. Excuse me. So let's see. Going back to your first page.
Sure.
So some important issues here that are general topics, excuse me, for high level, sort of a high level organization of taking this systematically, which I think it's great that you're doing this. I really like the phrase general systems context. I don't know how broadly that has been used, but it's interesting because it gets away from the question of, is it a theory, or is it, multiple theories, or it broadens that. So
yes, we will, so what we plan on doing is looking at this specific topic then in more detail next month, specifically talk about how it fits with systems concepts, systems hypotheses, systems framework, systems theories, and how it all fits to the scientific method and engineering approach. So yeah.
So then, very good. The question about time, excuse me. I think if one looks at, I believe it's Aristotle's Rhetoric, distinguishes the forensic view, which is backward-looking, the commercial view, which is forward-looking, and the maybe Helene knows this more, or you might know more, the celebratory, which is present-oriented. So more of a religious, ritual view in the present, or a forensic view in hindsight, or a commercial view to bind actions in foresight. I think that's so your issue here about the positioning with respect to time, I think it is, yes, it is. That should be pulled out as one of the top level topics to be explored. I do think that science is primarily backward looking. Science, it uses prediction as a form of test, but it starts from looking at what happened and trying to come up with theories to explain what happened, and then tries to, uses prediction as the form of quality control on the theory. So that would distinguish science from engineering, which is more commercial. It wants to bind, it wants to bind behavior in the future, whereas science is using the future as a form of quality control. Either of you anybody want to comment on that?
Well, those are really good points, Janet. And one of the things that I'm trying to do, in a more functional type of context is to say it's in the idea of discovery or design, right? So we use systems in two modes. We use them in a discovery mode, and we use them in a design mode. So that, and again, we'll talk about a little bit more about that in the next couple of papers, but the idea is to say, when you're looking at systems, or you're looking at data, or you're looking at something and you really don't know what it is, and you're trying to find out what it is, you're gathering data, you're getting research. That's kind of a discovery mode. And so I'm going to propose the fact that now that we introduce these two things, looking backward, looking forward, or right now, as you talk about what we're doing right now between those two, is that if I'm in a discovery activity, on what I really want to do is I want to reduce the complexity associated with the information or that activity. One of the things I can do, one of the ways I can do that is to reduce the uncertainty. So given a choice about some information or something I need to know about that system, I can look and I can say, oh, okay, I have developed a framework of concepts that logically allow me to infer this data, so I don't have to spend the resources to get that information, okay? Or I can move up to that point and say, well, I really don't know. I'm going to have to spend the resource to actually go get that information. And a third approach is to say, well, okay, I can develop a rule set now that says, well, if this happens, then that. Or if that happens, then this, right? Mm-hmm. But as soon as I start introducing that rule set, I introduce complexity. So
right.
These things will start trading off.
Right. Yeah, see, I think all of those are helpful, sort of complementary points. On the discovery design distinction, I think is really useful. And I would say discovery is primarily forensic. It's a matter of understanding what has happened, even if it's just right in front of you. It just happened, but it already happened. Whereas design is about binding the future. So that would go with Aristotle's forensic, commercial, hindsight, foresight distinction. So science would be primarily about looking carefully at what has happened, whether historically or right in front of you in an experiment. And engineering is primarily about binding, design, about binding the future.
Could I intervene here?
Please.
I find there's an interesting thing about prediction, because you have, I think, two types, or maybe more, but I kind of have identified two types that maybe sometimes are conflated. One is the forensic aspect. Is it you're Janet, right? Because I just see a J.
Yes.
Yeah. That you have brought about, which is projecting the past in order to predict the future. But there's another one which is probably also related to discovery, which is making the inferences, as Joe was evoking, from probabilities of interpretation of signs that you have in the data or in observations, and that could be a manifestation of something in the making, but that is not necessarily a projection of the past. And I think we need to distinguish these two types of predictions need to be distinguished, actually, because they're two totally different things. One is linear and projects from the past into the future, and the other one is more adaptive, because it kind of looks at what we have and makes inferences and probabilizes it as we go.
So
Right. I think the word retrodiction is useful there as well, to say if you're making if you're drawing an inference about something that already happened, then that can helpfully be called retrodiction, because there is no, there's a predictive element, because it's in the sense that you don't know yet whether you will turn out to be correct, but it's the retro and pre can be distinguished there.
Mhm.
Joe, what were you going to say?
well, it's a very, very interesting topic, and I think that it's a discussion that needs to happen. I think we flesh out the framework a little bit more with some, maybe pick 3 to 5 standard examples that we can actually talk more specifically about when we talk about these ideas. But when Helene was talking there, what reminded me, of course, was Tesla's epiphany in the park, right? So, something he'd been studying, he'd been thinking about this, he'd been doing all this stuff, he'd looked at all the previous science, and then he just basically had a vision that said, oh, this is the design. And he wrote it, took a stick and drew it in the mud or something. Well, that is kind of an example of what I think that Helene was trying to say, was that there's nothing really in the past that would predict this design for an AC current.
Mm.
So,
Well,
most
the notion is present is a bit, I mean, you can see the present in different ways. Like you can see the present as the continuation of the past, or you can see it as the seeds of the future. And
yeah.
and so I'm wondering if it isn't a paradigm difference here, and how do we get these two paradigms to coexist, actually?
Well,
Right. I think this whole topic here, the paragraph, introduces, the question in bold, and then the paragraph introduces one whole area to be elaborated, because I think there's a multitude of different ways of looking at time and sequence and determination and indeterminacy and things like that. Michael and I came across a really good article worked by an Indian physicist and historian of science who identified 12 different ways of treating time. And so it's a topic. It's good that it's called out, and it has various issues and questions that can be pursued later. But it is one of the issues here in this general modeling framework. Now, Helene, you also just raised the question of probability, so that gets into further on in the paper the relationship between the mathematical language and the natural language. So that's another fun, big topic that should have its own. I'm not sure what do we call this? High level category. There, maybe I'm not sure how many of those high level topics there are, but those are two excellent ones that are both very rich. Let's see, Michael, can you send Helene the Raju on 12 varieties of time? And maybe send that to Joe and Mary and Peter as well.
Okay, so
let's see. Just going back to the paper here. Let's see so then I guess the next topic you have there is the sensitive to human activities, which is maybe another high level topic. The then the next paragraph is the identifying components and structuring relationships. What do we have now? That's 4 high-level topics.
Yeah.
Then the excellent point about the minimizing resource utilization. So that's that's not a huge number of topics, but each of them is really key, and a lot of, like in the ontology work, they tend not to articulate that each of these needs to be given its own due. So that's a great framing. Let's see if I want to make I guess the final point I would make in this beginning work here is that in the conversations Michael and I have been having with Peter and Dwayne and Jennifer Wilby, we've been talking about how instead of general systems theory, it might have been better if they talked about general systems modeling, because the modeling is really the key. The modeling is where they were proposing an evolution or a more sophisticated view from the handful of the toolbox of the different approaches that were available at that point. And they were saying modeling, we need to understand modeling from all its in all of its facets, and the way the way it relates to reasoning and the way it relates to context and things like that. So I'm not sure if I think the work that you two are doing there, the general systems theory, maybe it's time to call this general systems modeling, and bring that to the fore, instead of the idea of theory, because you are addressing all the facets of modeling, which is great. So that's all I'd say on these first few pages.
Are there any other comments on the first few pages? Okay. Well, if any other comments, just make sure you jump in and we can discuss them. We have moved up to the types of truth. Basically, we're from Hall's Metasystems methodology. Hall's Metasystems methodology is mostly focused on human artifacts, the production and distribution of that. So it doesn't, it has a focus in man-made systems, not necessarily natural systems, but I believe some of the things can apply both places. But what is really interesting to me anyway is that it's important, I believe, like if you just look at the first 2 columns here, the formal column is where you'd say, well, this is where we're going to use inference or some type of approach to determine if something is true using calculation or logic without actually checking the facts or spending resources to do that. Second column, factual, is okay, we need to really go check reality, go check empirical scientific method to see what we believe is true. And then the value system, the third one is, well, we're saying, okay, no matter if these things exist or if they're true or false, what's the value? And the value is going to be in context. So the bottom row, I think, is again is one of the more interesting things, and that is that it's required to validate the inferences. The proof is necessary and sufficient. You can just do that proof fairly, following the rules, calculation fairly minimum outlay of resources, observational data and predicted success for the factual piece. That's more resources. And then for the value piece, it's no one kind of argument. So here you have to actually design the validation process, and which could include components of the other two. So in the value part, you really need to go through, and it could be a very resource-intensive type of approach to validate a value statement. Well, once we've done that, then we just kind of go through.
Joe, did you just say that the value, how are you relating value and context there?
Oh, so there's types of truth. There's formal truth, factual truth, and value truth. So if we were just to say, you know, examples here of the value truth, or John is a good man, John ought to pay $5, or John values gold, right? Those are statements about that truth, right? And, you know, what do they tell us, right? What do these sentences mean? Why do we use them? We say, well, they tell us what ought to be or ought not to be. They're values. And that evidence and relevance to their truth, meanings, observations, and value ethical systems. So that the thing that really comes into is the value ethical systems that are used in the validation of any one of these statements.
Mm-hmm.
We can have
so that is where context comes in, or
yeah, well, you could obviously, yes, the context there. If you have, you know, let's say different ethnic groups or different religious groups that have different systems of belief, they probably are going to have conflicts in their value ethical system.
Mm-hmm.
And so
I disagree, by the way, and maybe this came directly from Hall, but the John values gold is a factual statement. It's not a value judgment.
Well,
so I think that's not a good example of the distinction between a factual statement. You know, John is a man and John values gold are comparable factual statements. The others makes a value judgment.
Well, okay, so let's say John values gold. Let's say that's true, right? So how do we know that's true? So what I think I hear you saying is, well, our hypothesis is that John values gold. So it's a factual statement. So what we do is we go ask John.
Right.
John, do you value gold?
Right.
And John says, no, I don't.
Right.
So that's a fact, right?
Right.
So but the value statement, but it could be in other contexts where you could say, John values gold, and he uses it as the benchmark for his metric system. But I think it could be, as in many different categories here, they can be interpreted both ways. These are just kind of high level.
Mm-hmm. I think that one is it's an interesting. For example, I don't think, you know, one could say the same then about the others. You know, that John is a man could be a value statement. You know, so
a good man.
So John values gold is not a good way of showing the clustering, you know, the distances between these three types. But which is part of the problem of that we don't have really good methods and language for handling factual versus value statements. There's a tendency, I think, to assume that anything that talks about values is a value statement, and whereas one should be able to talk factually about, you know, the fact that people have values without having that be dismissed as non-factual. Anyway, that's a.
Isn't that because we're all, as you said, you know, using natural language? So what I find when I'm looking at various aspects of all these issues is that we tend to treat natural language at this, I mean, at different levels without necessarily knowing it. I'm not sure how to express this because it's just a kind of a hunch and a thought that's a bit evanescent here, but
Well,
we tend to confuse natural language as a means to something else, or natural language as the most important thing from which everything else arises. So I was interested in what's developed in this paper, and I don't really have the whole of it in my mind right now, but the fact of saying that you have mathematical language and you have natural language and you have the third, I don't remember which the third one, a meta language, I don't remember what the third one is, but
Graphic?
yeah, well, in the paper, probably graphic, yes. And so, yeah, there's something here about what's the representation of what. I mean, and I'm looking at that from the pattern perspective. So,
Mm-hmm.
yeah, it's not that easy to unpack the different, because
Well,
each thing that we're looking at is that it can have many personalities, let's say, or roles. It can be an end, it can be a mean, it can be a cause, and I think we need to try and find ways to announce or to make sure that we are all in agreement of which perspective we're looking at one thing at a certain moment. I don't know how to express this, but
Right. So maybe a cube would help, because you have natural language statements on the right there about, one is about facts, and the one on the right is about, well, let's see, what is it about? It's making value assertions, but it's through the means of natural language. So is that part of
the three columns here remind me of Aristotle again, where you have virtue, virtual, in terms of ethics. You have virtual ethics, which is the value column, and you have deontologic ethics, which is the formal, and then you have the means to the end, which is could be assimilated to the immediate factual factual one, and it also maps on the logic is the projection to the future, and the factual is could be the commercial, and I don't know.
Right, or the analysis of the past, or
yeah,
right, and purse also,
yes,
definitely would. So again, this is an excellent high level topic that sort of warrants its own unpacking.
Yeah, so the plan for the next paper is we're going to make greater use of our concept cube. And I don't know if people are familiar with it, but Mary and I developed a structure we call a concept cube, and which is mind compatible because it has the three components. And then we use that as basically a irreflexive, asymmetric, transitive type of decomposition network structure to start building the concept frameworks from which you develop hypotheses, and then you do your tests and so forth. And that's kind of one of the things we'll look at next month. So I think everybody's intuitively kind of right on.
Yeah, I like to think in terms of spheres, but they're maybe less easily manipulable because you don't know on which side or on which place you are at on a sphere. But
yeah, so I will distribute some of our papers on the concept cube and to the list so that people know. And the pointers, I think they're all out on ResearchGate, so maybe not all of them. Let's see, I can't really remember, but yeah, it's it's an idea that's fairly was developed in detail by the mind compatibility metrics. Were developed in detail by Warfield from other psychological and sociological data and experiments, and then we just kind of transferred those metrics to a graphical cube, and which we call the concept cube. And we'll talk a little bit more about that later on. So yeah, it's really nice stuff. Okay. So let's see. Shall we move along, or are there any more points here that people like to talk about? Okay, so let's move along here. So basically, after talked about the different languages and the types of truth, then we can look back at these statements by Boulding and look at them in terms of that context. So we're saying basically that there's the formal language constructs of pure mathematics, and because they don't need any semantic, contextual data to determine whether it's true or false, then it can apply anywhere. That's why, in a sense, that mathematics contains all theories and is the language of theory. Is the language of theory, though. I think it's a component of the language of theory. I don't think it's the total theory. You need to have a natural language component. I was reading the introduction to Turing's thesis, and he briefly talks about this when he talks about multiple sets of languages. Warfield kind of touched on it. You might expand that a little bit more, but you need natural language, because if you didn't, you'd have to have an infinite number of formal languages. So that's the piece where Warfield was talking about saying, well, yeah, you need to have carefully designed mathematical logic language, but you also need the natural language to cap it off, or you'd have to have a number of those.
And that's where the work on patterns can maybe help as a way to formalize things differently, but using a vehicle that can be used as a boundary object, and where people can exchange their views and perspectives on something that's captured in a let's say formal or semi-formal way, and then drawing some correspondences, like analogies between different ways of representing and seeing and describing things. That's what I'm specifically trying to work on.
Well, I think that's a great idea, because again, the human reasoning and logic capability is well known to be extremely limited, but our visual capability is very powerful. And so, that's why we're proposing the isomorphic languages, where you have the three languages: prose, structured graphics, and mathematics, so that you'll have a form. So if you have a concept that is encoded in prose and also encoded in structured graphics and is also encoded in mathematics, and that those three language forms are all isomorphic, meaning they mean the same thing, they mean the same concept, then you can look at that or understand or be able to assimilate information about that concept in three different ways. So we'll try to explain a little bit of that a little bit more, but that's essentially the work of Warfield in the science of generic design. He talks about the foundations for the physics and the physiology and their neural, the capability that human beings have for that design. So it's very good that you have a pattern. It's very important. And natural language patterns, depending on how formal they are a great place to to talk about or to represent or to actually communicate what that final piece is, you know. What is the part that cannot be done in mathematics? So went through here and talked about the different parts of the general systems theory. There's a quest to establish a single self-contained theory of everything, right? And I think this is the phrase that such a theory would almost be without content, for we always pay for generality by sacrificing content. And we can say, and all we can say about practically everything is almost nothing. So somewhere, however, between the specific that has no meaning and the general that has no content, there must be, for each purpose and each level of abstraction, an optimal degree of generality. And so discussion of that last sentence with Len is what prompted this paper. And the specific meaning, talking about meaning, right? So in natural language, meaning is by context. In formal language, meaning is by rules, right? So that's, to really unpack that statement, you have to realize the two different types of languages being discussed, mathematics and natural language.
But could I add that it's not necessarily only for each purpose and at each level of abstraction. You also have the eye of the beholder, and at equivalent degree of for equivalent purpose and equivalent level of abstraction, the optimum degree of generality may not be seen the same way. And this is where semantics and semiotics and comes into account as well, into the picture, and you need to unpack that as well.
Yeah, I agree. It's basically, but it is, when you're talking about an optimum degree of generality, when it becomes an optimization problem, then it becomes a value problem.
Mm.
It's when optimum is going to be determined by some value set, and value sets are going to be individual. So yeah. I agree. So,
yeah, so it's not general in the end. So the optimum degree of generality is not general and universal. So that's a kind of a paradox.
Well, it's okay. Well, let's unpack that statement a little bit. So the generality is kind of in the conceptual. When I think about general systems theory, I think about concepts, right?
Mm-hmm.
Not the general understanding, or everybody understands those concepts the same way.
Okay.
And so that, yes, we have these concepts that we say are general, and we propose and we encode these concepts in prose, structured graphics, and mathematics to try to increase the communication to a wider group of individuals. But those individuals, it may not be generally viewed the same. So the generality there is kind of two different concepts in my mind. So anyway, it's I would say the general systems theory must be based on a balanced combination of theories that occur with significant frequency in specific application domains. So I think this is kind of what Len has been doing. He's been out there looking at all these different specific application domains and finding things that are common, things that are different, same different type of thing, looking at those. And then I'm presenting a combination of both formal and informal languages. And so the formality, the formal component of the language really helps human beings from becoming overloaded with these concepts, just beyond our capacity to understand them. And then the informal language component augments the formal language by filling in the necessary semantics. So in context. So that's an important part. I think that kind of relates back to what Helen's saying about patterns can really help here. And there's just a lot of connection. But anyway, they said both Clear and Moorfield address these issues in substantial detail. Of course, then they could talk about the language types a little bit. We talk about the model exchange, isomorphism. This is just a high-level overview. The detailed parts of the graphics and the prose and the mathematics are in a paper out on the internet. And so essentially what we're doing here is we're just talking about one way to use logic to help engage large undefined systems that have a lot of components. So we can effectively do that. I won't try to go into all the parts of that, but in the abstract relation type, we developed this as a form for the prose, the graphics, and the mathematics. And so that the formal patterns, like from Alexander and from the computer science and so forth, those are basically formal, written out prose. And then you can have informal prose. And then we have directed graphs. And you can have formal graphs. You can also have informal graphs, sketches, and so forth. Anything to really help communicate the concept in mathematics and computer representation, equations, computer codes, and so forth. Yes?
So does it mean that you have a view of the pattern structure as a problem solution pair? Like Alexandrian and the whole pattern language view of patterns?
Well, yeah, you could. You could do that. You see, I should probably put. We have looked at the idea of in systems engineering of first developing a large set of alternatives before you pick a solution, right? So one of the ideas about the pattern for the Alexander is, says if I have this kind of problem, this is a candidate solution, right?
Mm-hmm.
But there could be many candidate solutions, and those are the things in systems engineering which we like to explore. We have a couple papers we did on that. I can also distribute pointers to those.
Yeah, that would be interesting, because this problem solution construction of a pattern, to me, that the pattern language community are having is something that stifles the progress and application of patterns. And it's something that we have been talking about within the pattern language community. So I was interested on how you deal with that.
Yeah, so there's a number of ways to deal with that, and I think that one of the primary ways is to understand that you can, when you identify a specific type of problem, right, and your problem, your solution, that is not necessarily a complete encoding of the current situation, and there could be many different solutions. And so that's those are the things that we wrote about in the past, published in the past. The details of that paper's not leaping to my mind right now, so I'll have to get those out there so we can discuss those if people wish. But I agree that the single problem, single solution is basically concerning. Well, yeah, I'll just leave it at that. There's certain levels of abstraction where it might be useful, but that's, again, a different issue.
But again, I think it's a distinction between whether you're looking at the act of design itself, So this is what patterns of pattern language are doing. They're creating a pattern that is going to act to guide the act of design itself. So they're basically solving a design problem and providing a recipe for getting from a design problem to a design solution, more or less. That I would distinguish from a systemic problematic or perspective that says, well, if I have a situation, what are the patterns involved in this situation, whether they are causal or structural or relational or whatever, or whether they are manifestations in a behavior. So this is something that you can discover, let's say. You discover your problem, and then you can design a solution which could be seen as an desired future way that the system is going to work. And in between the two, you have your active design of designing your system or your engineering product. And I think that's an important distinction to make between the systemic, let's say, phenomena that we may be observing and documenting and modeling, etc., and the design and the act of designing. And the interesting thing that also has been evoked in this pattern language conference where I presented the paper that we wrote with Peter was that the designers are mostly focused on how their design is going to behave and what the design is going to do, but they're a bit less involved on what their design is going to unleash as and generate as further systemic consequences into a broader system or into the context. And this opens up different ways of looking at things too, depending on whether you're just looking at something you want to design as an engineer, or if you're into systemic intervention and you want to study how a socio-technological system that is a composition or interaction between different designs, let's say human-made designs, can have its own life of its own and be tweaked or oriented or transformed. I don't know if I'm clear here, but...
Well, I think you're very clear, and it's a huge topic area. And one of the things we try to do is we try to keep our video conferences pretty close to an hour. And I just noticed that
yes, so I'll stop. Yeah.
To the conversation, it's a very interesting conversation. I neglected to announce it. I usually try to announce a 5-minute, but now we're already past. So I think we should take 3 to 5 minutes and kind of sum up here and look forward to the next conversation. And I will get some actions I've taken is I will get some papers out on the patterns and something else. Pattern paper and
the concept cube.
And the concept cube. Okay, I'll get those out.
Thanks.
Yep. Any other comments?
No, well, this is great, and it's obviously very good synergy with Helen and Peter's work, and so hope we can continue this in the 2-week call, or at least this broader discussion. Maybe Helen wants to present something, or should we leave that open?
Well, yes.
Why not? I mean, maybe not in 2 weeks, but at some point along the line.
Mhm. Well,
Also,
what
I'm putting here the link to my survey. I mean, my survey, is it? Oops. No, I didn't get the actual link. Just a second. On patterns, and to try and draw the pattern landscape. If you have a minute, it would be great to have your insights. And if you could help. Oh, why can't I? Oh, yeah, it worked.
Okay. All right. Is there any other final comments here, folks, before we kind of wrap it up for today?
So do you have any idea of what we'll do in 2 weeks then? So Helen, what we've been doing is we've been having the more structured discussions that Joe and Mary prepare a document for on the first Saturday. And then 2 weeks later, we have a more open-ended discussion where someone else can present. So that's what I was suggesting if you wanted to, or we can just continue the discussion you just raised there. That is, the tangential discussions that are related.
So what happened with the last unstructured presentation by Kevin was that Peter created a transcript. And so from that, what Kevin decided to do was to do a more formal presentation on the 17th. So I believe he's planning on doing a more formal presentation on the 17th, but there's plenty of time to figure that out.
Oh, no, that's excellent. That's fine. And is Peter's transcript available?
Yeah, sure.
Okay.
Yeah.
Oh, there you are, Peter. Okay.
Yeah.
So
I was going to say, one of the things that's come up, obviously, as we've gone through this, is a need for a number of threads, as I think Janet talked to them, or and Joe, you were identifying different sort of research topics that this higher level has taken, and I just wonder if there's a way we could summarize those particular, or if you've taken notes or go back and listen to this, maybe there's sort of a number of research topics. We really need a whole department of PhD students to follow up on. But I do think this is a wonderful beginning, if I can put it that way, to formalizing the foundational aspects of mathematics and its role in relation to natural language, and then graphics. As we think about the foundations for systems engineering based in system science, and we think about systems literacy from inception, if I can put it that way. So I think I'm really happy to see it.
Right, and the role of patterns as sort of a bridging, mediating idea.
Absolutely.
Yeah, and that's what I'm having my PhD on, actually.
Yeah.
Trying to see how patterns can help kind of bring some coherence and be a red thread, a kind of an underlying red thread between all kinds of different ways of doing, seeing, representing things.
Yeah, that's good.
Great.
All right, then. Well, that sounds great. So I'll get my paper out, my action items. If someone wants to do a topic summary that for the future, that's fine. Helene, if you want to propose topics for the future, just let us know, and we can just keep going forward.
Okay, great. Well, thanks for inviting me, and I'm sorry that I didn't quite understand or grasp from the beginning what it was all about and the format. So,
well, it's all fine. It's fine. Just keep going forward, and it's cool.
Good.
Good. Talk to you later then. Bye-bye.
Bye-bye.
Thank you.